Picture this. At the dawn of time, before the fiery spectacle of the Big Bang, a phase we call cosmic inflation took place. It was followed by a dance of quantum fluctuations, and then the Big Bang itself. As the universe cooled down and stretched out, it sprouted more matter than antimatter, and birthed stable protons, neutrons, and atomic nuclei. And then, when neutral atoms formed, photons stopped bouncing off free electrons, and for the first time, radiation could speed straight ahead, unimpeded, at the speed of light. Now imagine a bath of photons, the temperature at the start of what's known as the cosmic dark ages, a staggering 29,700.8 Kelvin, glowing a vibrant yellow-orange. The slight temperature differences in various pockets of space, pivotal to the universe's evolution. Overdense regions, heavy with matter and gravity, where photons lose more energy and appear colder, and underdense regions, with less of both, where photons lose less energy and seem hotter. Gravity, that irresistible force, pulls mass into these denser regions, yanking matter from the less dense areas near them. But there's another player in this cosmic drama: radiation. It pushes outwards, tempering the growth of these denser regions. So over cosmic time, our universe morphed from a uniform density to a tapestry of matter concentrations and voids. Then, during the cosmic dark ages, something fantastic happened. Hydrogen atoms began to emit light from the spin-flip transition within their atoms. This light, known as the 21-centimeter emission signal, comes from roughly 46% of all the atoms in the universe. It hasn't been detected from the very first atoms yet, but we know it's out there, waiting for us to pick up its signal with our advanced telescopes. The emergence of the first stars and galaxies. Oh, that's a crucial chapter in our cosmic story. Matter clumps growing slowly due to radiation pressure, until, when the universe was about 50 million years old, the densest clumps collapsed rapidly, birthing the first stars. The first grand star formation on cosmic scales happened when the universe was 200 to 250 million years old. But the conditions before these first stars were born, they were vastly different from today. Space was packed with neutral, light-blocking atoms, and the residual glow from the Big Bang, known as the cosmic microwave background, was hotter. Now here's the twist. Despite our powerful James Webb Space Telescope, we may not be able to directly observe these very first stars. The first star formation remains a mystery, and the universe stays dark until, well, you'll find out soon enough. Hey there, curiosity explorers. Ready for another dive into the unknown? I'm Caesar, your guide on this cosmic journey, and with me is the one and only Sonia, our resident commentator and cosmic detective.
Hello, fellow explorers. Together, we're going to unravel the mysteries of our universe, one curiosity at a time.
And we can't do this without you. Your thoughts, your questions, your curiosity, they're what fuel this journey. So hit that subscribe button, leave a comment, share the Curiosity Wonderland with your fellow explorers. We're on this journey together, and every voice matters. Let's dive in, shall we? It's fascinating to think about the early stages of our universe, isn't it? Before the hot Big Bang, before the first glimmers of starlight punctured the darkness, the universe experienced cosmic inflation, giving rise to quantum fluctuations. As the universe expanded and cooled, it produced more matter than antimatter, then stable protons and neutrons, and eventually neutral atoms, all against a backdrop of radiation and neutrinos. Despite what we might imagine, the formation of stars didn't occur immediately after neutral atoms formed. The universe needed time, a lot of time, somewhere between 50 to 100 million years, for even the first star to form. This prolonged period, devoid of stars, is what we refer to as the cosmic dark ages. When the universe transitioned from being a sea of ionized plasma to a neutral state, it allowed photons, particles of light, to travel unimpeded in a straight line at the speed of light. It was like the curtains had been lifted, and light was allowed to dance freely across the cosmic stage.
You know, this reminds me of a personal story from my childhood. As a kid, I was fascinated by glow-in-the-dark stickers. I had a collection of them, and I'd stick them all over my bedroom walls and ceiling. But of course, they needed light to charge. So, during the day, they'd soak up all the sunlight, storing energy. Then, when I turned off the lights at night, my room transformed into a miniature universe with all these glowing stars twinkling in the darkness. Looking back, I realized that my bedroom was like the early universe. During the day, it was like the hot Big Bang, full of light and energy. Then, when I turned off the lights, it was like the cosmic dark ages, and the glow-in-the-dark stickers were like the first stars, taking their time to form, soaking up energy before finally shining in the darkness. It's a simple comparison, but sometimes the grandeur of the cosmos can be reflected in the smallest corners of our everyday lives.
Following our cosmic timeline, the light we're talking about vastly outnumbers the atoms in the universe. It's omnipresent, coming uniformly from all directions. At the start of the so-called cosmic dark ages, this omnipresent light was at a temperature of 2970.8 Kelvin. Picture this as a yellow-orange hue. Now, some regions were slightly hotter and others slightly cooler by fractions of a degree. But don't be fooled. These seemingly insignificant temperature differences play a critical role in shaping the evolution of the universe. Imagine this sea of photons, particles of light, each carrying the same amount of inherent energy. However, the environment in which they existed varied from place to place. Some regions had the average universal density, while others had more or less matter. The regions with less matter had less gravity. Consequently, when a photon left such a region, it had less gravitational potential to fight against, and therefore lost less energy. This leads to a photon temperature that appears hotter than average. Conversely, regions with more matter had more gravity. Thus, photons leaving these areas had to fight against greater gravitational potential and lost more energy. This resulted in these photons appearing colder or less energetic. It's fascinating to realize how these subtle differences in density and gravity across the universe influenced the energy and perceived temperatures of photons, and consequently shaped cosmic evolution. So if we picture a universe that consists of regions of average density, regions of greater than average density, and regions of below average density, we might assume that the overdense regions would attract more matter due to gravity, eventually forming the stars we see in the night sky. That's a crucial part of the story, but it's not everything. Gravity, in essence, is somewhat of a runaway force. The regions with the most mass attract additional mass from nearby regions. The areas that had an initial advantage are the ones that end up with most matter in the end. As more matter is attracted to a region, gravity becomes even more successful at drawing in even more matter. However, we can't forget about the radiation, the remaining photons from the cosmic background. While matter, both dark and atomic, lures in other massive particles due to gravitational attraction, it also draws in all forms of energy, including radiation, into the most overdense regions. So matter and gravity were not the only forces shaping our universe during this period. The leftover background of photons also had a significant role to play. It's a complex dance, with multiple forces at work, each contributing to the grand evolution of the cosmos. Now, when we talk about radiation, we have to remember it has a significant amount of pressure. Take our sun, for instance. It's less dense than our planet, even though it has 300,000 times the mass of Earth. This is due to the enormous outward pressure exerted by photons inside it.
So, the same pressure that keeps the sun from collapsing also affects the growth rate of gas clouds before stars are formed.
Precisely. Even in a universe dominated by matter, growth is slowed down when radiation still plays an important role. This outward pressure limits how quickly these matter overdensities can grow.
What happens then as time progresses?
With time, gravitational interactions transform a mostly uniform universe into one with large conglomerations of matter and vast voids separating them. But for as long as radiation is significant, the growth of these matter clumps is minimal.
And this process goes on for millions of years.
That's right. The radiation pressure simply doesn't allow the matter density to increase faster than a particular rate. And during these millions of years, as the matter density slowly increases, another process begins to take place involving hydrogen, the most common atom in the universe.
You mentioned earlier that there's a new form of light that gets emitted?
Indeed. After neutral atoms are formed, mostly from protons and electrons, the light from the spin-flip transition within hydrogen atoms gets emitted. During these dark ages, 92% of the atoms in the universe are simple hydrogen.
What happens during this spin-flip transition?
Hydrogen atoms comprise one proton and one electron, and both possess an intrinsic spin. There's a slight difference in energy between a system where the proton and electron have the same spin versus one where they have opposite spins. Over a period of around 10 million years, the configurations with the same spin will spontaneously flip, emitting a photon of a specific wavelength, 21 centimeters. It's quite a fascinating process. Now, this hydrogen spin-flip transition is astonishingly precise, measured to better than 1 part in a trillion. This light was the first emitted in the universe after the formation of neutral atoms, before the formation of the first stars.
So there's another signal on top of the cosmic microwave background radiation from the Big Bang?
Yes, exactly. This is a weak signal from the 21 centimeter emission line. If 92% of the atoms are these simple hydrogen atoms, and there's a 50-50 chance of protons and electrons having initially aligned or anti-aligned spins, then approximately 46% of all the atoms in the universe should emit this 21 centimeter signal.
And this signal occurs every time new hydrogen atoms are made.
That's right. Every time a hydrogen atom forms with aligned protons and electrons, it will emit light in this manner. While we haven't yet detected this emission from the very first atoms formed in the universe, we know how to predict it, and a sufficiently advanced radio telescope should be able to detect it.
And this is the only process happening at this stage in the universe.
Actually, no. There are other simultaneous processes that are crucial to the cosmic story that's only just beginning to unfold. While it's true that normal matter, the stuff that makes up all the stars, planets, and all the chemical reactions, is arguably the most important from our human perspective, there's more to our universe.
What else is there besides this normal matter?
There are a few things we need to get from the formation of neutral atoms to the creation of stars. We need photons to redshift, gravity to pull matter into overdense clumps, and time for these effects to build and have substantial impacts. The cosmic dance is far from over. Over the first 3 million years after neutral atoms form, the temperature drops from around 3000 Kelvin to 800 Kelvin. This change takes the radiation from yellow-orange to orange, then red colors, until it finally cools enough to become invisible to human eyes.
So what does this mean for the formation of structures in the universe?
Well, the decreasing radiation pressure allows matter clumps to grow, but only to about 4 times the magnitude that they were when the cosmic microwave background was emitted. The growth of these overdense regions is limited by both their initial small sizes and the presence of still energetic radiation.
And what happens as the universe continues to cool and expand?
By the time the universe is between 15 and 20 million years old, it's cooled to around room temperature, as we know it here on Earth. The matter clumps that were just a bit denser than average have grown significantly, becoming about 10 to 15 parts in 30,000 denser than the cosmic average.
So does this mean the denser clumps start to grow faster?
Yes, exactly. The densest clumps start to grow somewhat more rapidly, becoming about 60 to 90 parts in 30,000 denser than average.
So what happens when these clumps reach a certain density?
That's a great question. There's a critical density that these matter clumps can reach, where their growth no longer follows a straightforward law. This is what we call the nonlinear regime of structure formation, where clumps start growing much more quickly once they become about 68% denser than average.
What does this mean for the evolution of the universe?
This marks a critical transition. After this point, runaway collapse becomes inevitable. The first stars and galaxies in the universe will be surrounded by neutral atoms of mostly hydrogen gas. Our best theories of structure formation suggest that the very first star likely formed when the universe was 50 to 100 million years old. Around 50 million years after the formation of neutral atoms, the densest matter clumps transition into the post-critical phase. These clumps start contracting and drawing additional matter in at an accelerated rate.
So, does this lead to the formation of the first stars?
Yes, exactly. The absolute densest regions of space will rapidly lead to the formation of the first stars. However, the rest of the universe grows more slowly, requiring more time for the matter clumps to reach densities where star formation is possible.
When do the first big waves of star formation occur?
For most parts of the universe, the first major waves of star formation don't begin until about 200 to 250 million years old. However, within the very densest regions, matter collapses down to large densities in just 50 to 100 million years.
What conditions need to be met for the first star to form?
At some point, the first hydrogen into helium chain reaction via proton-proton fusion will occur, marking the formation of the first star. The universe needs to cool to somewhere around 100 Kelvin before the first true star can actually form.
How are the conditions in the universe just before the first stars formed?
Space wasn't transparent to light at that time, but rather was filled with neutral, light-blocking atoms. The leftover glow from the Big Bang was about 30 to 50 times hotter than it is now. Even with the powerful infrared capabilities of telescopes like the James Webb Space Telescope, we cannot observe these conditions.
So the very first stars remain a mystery, even to our most advanced technology?
That's correct. Despite many hoping that the JWST will enable us to directly view the first major waves of star formation, the very first stars should remain obscure, even to its extraordinarily powerful eyes. It's a testament to how far we've come, and yet how much more there is to discover. Until the formation of the first stars, the only light in the universe was the leftover glow from the Big Bang. After just 3 million years, this light falls to such low energies that it becomes invisible to human eyes.
So this means that there was a period in the universe's history that was completely dark?
Exactly. For around 47 to 97 million years following those first 3 million years, the entire universe was truly dark.
And then the first star ignited?
Yes. Once the first star ignites, let there be light becomes once again a part of our cosmic history. This signifies the end of the dark ages of the universe and the beginning of a new era of stellar formation and illumination. It's a literal and metaphorical renaissance, a rebirth of light in our cosmic history. To quickly summarize, we've journeyed through the early stages of the universe, looking at cosmic inflation, the formation of quantum fluctuations, the hot Big Bang, and the formation of neutral atoms. We've explored the cosmic dark ages and the role of gravity and radiation in the evolution of the universe. We've learned about the 21-centimeter emission signal and its potential to reveal secrets from the universe's past. We've also delved into the formation of the first stars and galaxies, and how, after a period of utter darkness, the ignition of the first star marked the end of the dark ages and brought light into our cosmic history.
It's an incredible story, a testament to the wonder and mystery that our universe holds. Thank you, listeners, for joining us on this journey through the cosmos. If you enjoyed this episode, don't forget to blast that like button.
And please take a moment to share this episode with your friends and leave us a comment. We love hearing your thoughts and questions.
We're signing off now, but we'll be back with more cosmic mysteries soon. Until then, keep looking up and wondering about the beauty of our universe.
Goodbye, listeners. Keep joining us on these journeys of discovery.
Goodbye, everyone, and remember, the universe is full of mysteries waiting to be uncovered.
This cosmic journey was inspired by an article titled, "What Was It Like When No Stars Yet Existed?" by Ethan Siegel on the Big Think site, published on December 14, 2023. You can find the full URL in the video description if you want to delve deeper into the subject. Now, I'm off.